Hello everyone, and welcome to this web demo about the manufacturing of helical gears in KISSsoft. My name is Martin Kohler. I work in the support team at KISSsoft AG, and I will show you some of the functions in KISSsoft in the following hour. My colleague Jörg Langhardt sits next to me and will answer the questions you write to us during the web demo. We will then look through some of the questions together at the end of the web demo. On our website, you can also download the handouts related to this demo. Now, first, we are going to look at the content that we will be going through together. We will begin with manufacturing of a helical gear with a hobbing cutter, meaning that we are first going to look at the single manufacturing step, where we are going to see what kind of influences we have on the manufacturing profile shift. We are also going to see how we can define a topping tool. Then, after we have covered all the basics, we will go to the next topic, which is that we add a final machining stock. So we switch to two separate machining steps, and we will see what kind of adjustments we need to make on the pre-machining tool to take this machining stock into account. And finally, at the end, we will save this pre-machining tool in the database. I will open the software, and for this demonstration, we will use one of the examples that are pre-installed in KISSsoft. You can find the examples here on the bottom left. So we will open the cylindrical gears, and we will choose the single cylindrical gear. What we are going through today is also valid for gear pairs or planetary gears, but it is a bit more simple if we look at it on a single cylindrical gear. Now, this gear example, if we open the tooth form graphic, we can see, as we can also see in the basic data tab, this is a cylindrical gear with 17 teeth, and at the moment it has a normal module of 1, which I will first change to a module of 2, so we can more clearly see the difference between what is a length in millimeters and what is a coefficient or a factor which is multiplied with the module. So this gear, besides what we can see in the basic data tab, it will also be defined by the settings in the reference profile. We can see here for the tool, what is selected at the moment is reference profile gear, which means that the coefficients, so the dedendum coefficient, addendum, they are defined directly for the gear. But in the background, there will always be a cutter that is generated, which is then used to simulate the machining process to create the gear that we can see on the bottom right here. We can also show this cutter if we go to Geometry 2D and go to Cutter Tool. So this is this cutter that is automatically generated in the background. So even though we enter the reference profile for the gear in the background, it will create a cutter which then cuts our gear. Now, if we want to be more specific about the cutter geometry, instead of using reference profile gear, then we should switch to hobbing cutter, which will allow us to more precisely define this cutter. If I select hobbing cutter, it will convert this data, and I can now see at first it still looks very similar. So I still have an addendum coefficient, dedendum coefficient, and a radius. But now the main difference is that this addendum means the addendum of the cutter. And the dedendum is the dedendum of the cutter, not of the gear. And what has also changed is that now I have to separately enter the addendum coefficient of the gear itself. If we look at, let me calculate this first. If we look at the manufacturing graphic where we can see how this cutter is used to cut the tooth form. So I go to Geometry 2D, Manufacturing. So here we have both of these together. And we can see that by default, we do not have a topping tool. So the cutter, the addendum of the cutter will directly define the dedendum of the gear, but the dedendum of the cutter does not define the addendum height of the gear. So this we have to select separately down here. What we can also do in this graphic, we can check whether those inputs that we have in the reference profile really correlate to what we can see in the graphic. And we can do this by right-clicking in the graphic and choosing the measuring tool. If I go in here and measure from this dotted line, which is the reference line of the cutter, if I measure from here to the root of the cutter, I can see I have here let me calculate this again. Okay. One second, let me check another graphic. Yeah, I have here in the root. Right, this is the dedendum, so this gives me the root height of the cutter, and I have to multiply this dedendum coefficient by the normal module. So for the dedendum, this would mean that the root would be 1.2 times 2 millimeter, so the dedendum should be 2.4 millimeters, which I can also measure here. For the addendum, I have a factor of 1.25, so if I multiply this with 2, I should see a tip height on the gear of 2.5. So if I go in here and measure this tip, I will get this 2.5 millimeters. And the tip radius that I enter here is the radius at the tip of the tool. So now we know how this reference profile is defined. The next question would be, when we now want to use this cutter to manufacture this gear, we have the geometry itself, but where do we position this cutter? So in this graphic, the question would be, what is the vertical positioning of the cutter during manufacturing? And we know we have this reference line of the cutter, and a first thought may be that this reference line would then align with the pitch diameter of the gear. We can add the pitch diameter to our graphic, or the reference circle, and we see that this is not the case. So the reference line of our cutter does not match the pitch diameter of my gear. And this difference that we are seeing between this pitch diameter and the reference circle, this is the manufacturing profile shift. And I'm now going to show you the reason for this manufacturing profile shift, or where this is coming from. The first reason, as you probably know already, is our gear itself has a certain profile shift, which we can enter in the basic data. And this profile shift, with this one, we can change the tooth form, and this is in the end manufactured by moving away the tool further by a certain amount. So a positive profile shift coefficient here means that the tool will be moved away a bit further from the gear during manufacturing. I will set this one to 0 so we can look at it, how it would look without the profile shift. But before I calculate, I also want to show you the second influence, which are the tolerances. We have this tolerances tab where we can define a tooth thickness allowance, an upper and a lower allowance. And those allowances mean that we make our tooth a little bit thinner than its theoretical thickness. And we do this to create a certain amount of backlash in the gears. We can see we always have this upper and lower amount, and what we have in the graphic in the end by default is in the middle of those tolerances. We can also adjust this down here. We can see for tooth thickness we can choose between mean value, nominal, so the theoretical tooth thickness, or minimum and maximum. But by default this is set to the mean value. And those tolerances or those thickness allowances, they are created by moving the tool a little bit further into the gear when we manufacture it. This will create a slightly thinner tooth. If I remove those tolerances, if I set it to no backlash, they will be set to 0. And if I run a calculation now, I will see that now, in this case, my reference line of my tool would match the pitch diameter of the gear. And if I reintroduce the profile shift again, so I add this 0.3 and run a calculation, I see the tool will be moved out, and this distance, 0.6 millimeters, is exactly the profile shift coefficient multiplied with the normal module. And if I reintroduce the tolerances, and run a calculation again, you will be able to see how our tool moves a little bit further into the gear again. So I run the calculation and the tool has moved a little bit further back into the gear. What we can also see in this tolerances tab is that for the tip diameter allowance, here we have separate manual inputs. All the other inputs here for thickness allowance and also for root diameter allowance, these are now automatically entered based on which tooth thickness tolerance I select up here. So those are all dependent on each other because the flank and the root, they are generated in the same step. But the tip diameter allowance I can machine in a separate step because I'm not using a topping tool at the moment. We can also look at what it would mean if we would change to a topping tool. For this, we go to the reference profile, and down here we can see a selection for topping tool. If I select this topping tool, then this manual input for the addendum coefficient, with which we are able to separately define the tip height of the gear, this will disappear. So I activate this flag, and if I now run a calculation, then the root height of my cutter will define the tip height of the gear. So we can see now the tip height of the gear, or the tip of the gear, will be cut with this cutter in the same step. This also means when we look in the tolerances that now we cannot separately define the tip diameter allowance anymore. This will also be directly connected to the tooth thickness tolerance. And we can see the tip diameter allowance is now the same amount as the root diameter allowance, because again it will be cut in the same step. If I want to go back again to not using a topping tool, I can remove this flag, and now I could enter the tip height separately again. What I have to be careful here now, if I switch back and forth, is that in the tolerances tab, it will not automatically change back to those allowances I had before I used the topping tool. It will leave those inputs, or it will stay at the last inputs that were in here. So in this case, I would now have to manually enter the previous allowances again to make sure that I now have the same gear again as I had before. So we have now seen that whether you choose a hopping cutter in the reference profile or the reference profile gear, it will always create a cutter in the background and use this cutter in a manufacturing simulation to create this gear. And if we select the hopping cutter, then we can directly define the reference profile of this cutter, the root height, the tip height, and all the radii. And we have seen what influences there are when we manufacture it, how far we position this cutter into the gear. So what is the manufacturing profile shift in the end. This was everything so far about the first part, about a single manufacturing step. What we are now going to do is we will switch to a pre and final machining step. Before we do that, I will save the gear that we have right now so that we can later compare it. So in the graphic settings, I will choose this gear and choose to save the curve. I can give it a name. I'm going to call it the original tooth shape. I will select the dark gray dashed line. So now we will always be able to see this dashed line where our original gear was. And now to switch to two separate manufacturing steps, where in the first step we will leave some amount of machining stock on the flank, and then in a second manufacturing step we will grind away this additional machining stock. What we have to do is we have to go to the reference profile tab, and here we can see at the moment at machining step it is selected to be final machining without pre-machining. So the reference profile that we have entered down here is also directly the final machining reference profile. If I now want to have two machining steps, then first I have to add this machining stock. So I click up here, and I could now manually enter a certain amount, or I just choose manufacturing stock according to standard. I will now get the warning telling me that I may have to do some additional adjustments to my pre-machining tool. So after I have activated this, I can now see that it has given me this final machining stock of 0.11 millimeters. And what has also changed is that down here we still have the same reference profile, but this is now our pre-machining reference profile, which we can also see on the top left here. I will now run the calculation without changing any additional settings, so we can see how only adding this machining stock will affect our tooth shape. And we can see in our manufacturing graphic, we get a lot of additional lines. I'm going to remove them now and add them back individually so we can look at each one of them. So at the moment, we still have our original tooth shape, which we had before. If we now look at the pre-machining tool, this is the same tool that we already had before, but we can now see that during manufacturing it has been moved away a little bit more from the gear, which then will give us this tooth form after the pre-machining. So we can see we have created if we go in here and measure, we have created this additional machining stock on the gear of 0.11 by moving the tool out in this graphic vertically up. This is the pre-machining step. If we add this machining stock, then automatically it will also create a final machining tool for us. And we can see this in the graphic. So this is the final machining tool that we have now. And we can see how this final machining tool will grind away our flank, but we can also see that it doesn't touch the root diameter. This final machining tool, as I said, it is automatically created, and in the final machining tab you could also add some adjustments to how this final machining tool is supposed to look like. What we will now focus on is we will try to achieve the same tooth shape as before, because if we look at the tooth form after the final machining, we are still looking at the tooth form before final machining here, so I will also show the tooth form after final machining. We can see that after final machining, this machining stock on the flank is gone, but we are still left with some additional material down here in the root. We can see we have a different root diameter now, and we can see that on the left and on the right we have those notches appear, which would affect the root strength negatively because we have a much smaller radius here in those notches. What we will do now first is we will try to achieve the same root radius again as we had before. And the way we achieve this is we will take our pre-machining tool and we will increase the length of the addendum of our pre-machining tool so that it will reach down to the same root diameter again. This means that we will have to adjust the addendum coefficient of this tool. Now the question is, by how much do we have to increase this addendum coefficient to get back to the same root diameter? There are multiple ways how we could do this. One way would be that we look into the report, we read out the manufacturing profile shifts of the tool or the manufacturing profile shift that we had before without the machining stock and the shift with machining stock, and this would tell us how far further this tool has been moved out, which would then be the amount that we need to add to the tip again. Another way would be an analytical way. We could look at our final machining stock, and based on the pressure angle, this would allow us to calculate by how much this tool had to be moved out. The most simple way, the easiest way, which we are going to do now, is we can go back to the original calculation and read out the root diameter that we previously had, and we can then use this root diameter and use an automatic recalculation function to find out what addendum coefficient we will need on this tool. So I will remove this machining stock again for a second, run a calculation, and I will go into the report. In the report, I will go to the root diameter, and what we have here is the theoretical root diameter. And just as additional information, in here we could also see the root diameter at upper and lower tolerance limit. But what we need for now, or all that we need for now, is this theoretical root diameter of 30.2. So I will add my machining stock again. And I will now enter, or I will now use this previous root diameter to adjust the addendum of this tool. For this, we have a very convenient function here. For the addendum coefficient, we have a conversion button. If I click on this, it allows me to directly enter the diameter, the root diameter I want to achieve. So I want to achieve the old root diameter again, so I enter 30.2. I press calculate, which will give me this addendum coefficient for the tool. I accept, which will automatically transfer this value into this reference profile input window. And if I now run a calculation, you will see in the 2D graphic how the tip of the tool has now become longer, and we now achieve the exact same root diameter as we did before. But if we look closer at this graphic, we can still see that even though we now have the same root diameter, we still have those notches left over on the left and on the right side. So we have left some of this additional material here in the root on both sides. We have left this over. And as mentioned before, those notches will negatively affect the root strength, so we should remove this additional material here. How do we remove this material? One thought that you might have is we now increase the tip height of the pre-machining tool, so maybe we could now increase the tip height of the final machining tool to grind down this additional material in the root. However, this is not recommended, because if you grind down all the way into the root, you may cause an overheating in the root when grinding. And this overheating can then negatively affect the material properties in your root area, which then in the end will negatively affect the root strength. So we do not want to grind all the way down into the root. Instead, what we will do is we will make one further adjustment to our pre-machining tool. And what we will do is to remove this amount on the left and on the right. We will make the tip of our pre-machining tool a little bit wider, so that it can cut away this area here. Making the tip of the pre-machining tool wider, this is called a protuberance. And if you look in the reference profile tab, if you go to this info button on the top right here, it will show us an information graphic about the tool. And in here we can see an example of a protuberance, and we can see that there are two coefficients which define our protuberance. One coefficient is this protuberance height, which we can see over here. It will define the start of the protuberance, so the start point where the tip of our tool becomes to be thicker than if it would stay at the same angle. And the angle itself is the protuberance angle, which we can see over here on the left. This angle, similar to the pressure angle that we see down here, is defined from a vertical line. so it will be a little bit less than our pressure angle. Now the next question becomes, or first let's look into the reference profile. So in here we can see that the protuberance height coefficient and the protuberance angle, these are the two inputs that we have to define our protuberance. But the question now is, what should be the protuberance height? So at what point should my protuberance start, and what angle would it need to remove this additional material down here in the root on both sides? And this would be difficult to directly enter in here. But for this, we have a very convenient conversion button, which we can find next to the protuberance height coefficient. If I click on here, I can see that I have the possibility to convert the protuberance height coefficient from the protuberance and protuberance angle. Now the protuberance, this is not the same as the protuberance height coefficient. The protuberance is the actual amount by which we make this cutter thicker. So we could simply enter the final machining stock in here, but we will not exactly use this amount because actually we want to take away a little bit more than what we see in this graphic. If you remember, I previously mentioned that what we see in this graphic is always at the middle of tolerance. But if you take away exactly the same amount, or if you would now take away exactly this amount, then there may be tolerance situations where in the end there would still be a certain, or there would still be a notch left here. So what we will do is we will try to more go towards taking away a little bit too much material. This will cause a slight undercut in this root, but to have a slight undercut would not affect the root strength as negatively as a notch would affect it. Because with a notch we immediately get a very small radius. So what I will do is I will choose a slightly larger amount for my protuberance, and for the protuberance angle here there are different possibilities. In this example I will use a protuberance angle of 10. I run a calculation for this conversion and this gives me my protuberance height coefficient. If I press accept, it will now take those coefficients, or this coefficient and this angle, it will take it into my reference profile. Now let's run this calculation and see what happens in the graphic over here. And we can see we now got this protuberance in the tip of my tool, and we have successfully removed this notch over here. We can see because we have used a bit more protuberance than the only enough to remove the machining stock. We have used a little bit more, so we can see that also down here there's a little bit an undercut compared to the original tooth form. But again, it is better to have a slight undercut than to end up with a notch in our root. So now what we have ended up with is our tool, our pre-machining tool, in which we have changed the addendum coefficient, so that even though we have moved it further away to create the machining stock, we still get the same root diameter, and we have added a protuberance to eliminate this notch that would be left over after grinding. We can also look at the second machining step again. So what we would have is, after the pre-machining tool, what we would have is we would be left with this amount of machining stock on the flank, and we can see this undercut that we have created with our protuberance. And then after the final machining step, so with this final machining tool, we would grind away this additional machining stock, and we would end up with our final tooth form, which we already saw before. So now that we have created this pre-machining tool, we might want to use this later again. And one way, of course, would be to take note of all these inputs, and then if we need them again later, enter them again manually. But of course, this could be inconvenient, especially if you have different or a larger selection of different cutters. You don't want to manually have to enter all those values again. Now in KISSsoft, besides entering the values as own input, if you look up here next to data source, you can see there are some cutters already available. And what we will do now is we will create our own database entry and create our own list of cutters, which will be connected to this database entry. The data structure to save this tool looks like this. We have, as we see in the bottom right here, in our installation directory where we have KISSsoft installed, we can save a list of our cutting tools. So we will create a new list for this cutter that we have just created. And this list will then be linked to an entry in the database tool. So we will also look at this. We will create a new entry in the database tool and link it to that list. If you have no list yet, the easiest way is to take one of the already existing lists and create a copy of it. I will show you this now. I will go to my installation directory, and here in the installation directory there's a folder, the .dat folder, and in here there's a large amount of different lists and tables which will be used by different databases. What we need right now is the Z000 DIN 3972. This is one of the two already existing lists that we have in here in this .dat folder. I will copy this one, and now when I create my own list, I will not create it in the .dat folder, because this .dat folder only contains the default lists. If I want to have my own lists, I have to go into another folder, which is this ext folder. And inside the ext folder, there's another .dat folder. And this ext .dat folder, this is the place where I can store my own lists. So I will paste the list that I've just copied into here. I can give it a new name, for example, own cutters 02. And now I can open this list with a text editor. Yeah. And in here, what I see now is the previous list, the default list. Right now I only need one entry, so I remove the rest of this list and I will adjust the first entry of this list. On the very left, we can give each cutter a name. So I can call this cutter the web demo cutter. And then in those columns here, I can enter the normal module, in our case 2. And then I can go through the rest of these columns. So the next one is the pressure angle. It's also 20 degrees in our example. The addendum coefficient, which in our example is 1.4108. Then we have the tip radius coefficient, which is 0.38. Next one is the dedendum coefficient, which is also 1.2. And the next two columns are for the protuberance height coefficient and the protuberance angle. Our height coefficient is 0.6215 and the protuberance angle is 10 degrees. There are some additional columns back here which we will now not look at in detail. They are related to inputs that you need or that you could use when you use those cutters during the fine sizing or in connection with a fine sizing function. In a fine sizing function, you would also have the possibility to restrict the solutions that the fine sizing function will give you to a specific list of cutters. So if at your company you have a list of cutters that are already available, then you can also enter those cutters into your own list like we are doing right now. And in the fine sizing, you could then manually, or you could then tell the fine sizing function to only use those cutters. But this fine sizing function we will also not look at in detail during this web demo. What I will do now is I will save this list, which at the moment only has this single entry. And the next step will be that I go to the database in KISSsoft. I have to open it with write authorization, and I will scroll down to the selection of hobbing cutters, which I can find down here, selection of hobbing cutters. And I can see in here there are the two default lists and some additional lists that I have created. To create our new list now, I will click on Own Input, and with the plus button down here, create a copy of this entry. I can give it a designation, which I can call, let's say, own cutters. So this designation does not have to be identical to the name of the list that you have in the installation directory, but you will then have, under file name, you then have to select that list. If I click on this button here, it will directly bring me to the ext.dat folder in the installation directory, and here I can select this list that we have just created. So I open this, and now I have linked this database entry with that list of hobbing cutters. I confirm, save, and close. And now I can already, under data source, instead of choosing own input, I can select own cutters, which is the database entry that we have just created. And if I click on this, it will show me a list of those cutters which are available for this module. If I have multiple cutters in this list with different modules, by default it will only show me those cutters with the same module. I could also remove this flag up here and it would show me all the cutters in this list. To use this cutter, I will click on it and confirm with OK. And I can now see, I now see the designation of this cutter that I gave it in that list. And I can see all those coefficients are now automatically entered based on what is entered in that table. I can run the calculation again and see nothing has changed in my graphic. So I have successfully saved this cutter in the database. So what we have seen in this web demo is we have seen how the reference profile works, how in the background there's always a cutter that is generated that if I select the hobbing cutter as a tool, I can manually define every coefficient of this cutter. Then we have added a final machining stock up here, and we have made adjustments to the pre-machining tool by increasing the addendum coefficient so that we get the same root diameter, and we have added a protuberance using this height coefficient and angle and the conversion button for the height coefficient to eliminate the notch in the root area. And at the end, we have seen how we can save a certain tool in the database. So this was it, or this was it so far for the content of this web demo. We will now look at one or two questions that have come up during the web demo. So one question was to explain the analytic method that I mentioned to determine the additional amount of tip height on the cutter. I can show you this again. I will let's see, I will remove this own cutter again, set it to own input. So what we had before was a shorter tip height. This was, I think, 1.25. Now the additional amount of addendum, this is directly related to this final machining stock, because to create this final machining stock, we have vertically moved this hobbing tool further away from the gear during manufacturing. And this additional machining stock, if we measure it, we will find it has this amount of 0.11 millimeters, and the additional amount that we had to move our tool vertically would be this vertical amount here. And if we look closely, we can see this amount here, this amount normal on the flank, and this vertical amount, this is related through a sine of the pressure angle. So if I would do this, if I would want to get this vertical amount analytically, what I could do is I could open a calculator. This would also be possible to enter it directly on KISSsoft, but I will open a calculator separately. I can take my final machining stock, so 0.11, and I can divide it by the sine of those 20 degrees pressure angle. This will give me the amount in millimeters, so I still have to divide this by the normal module to get the amount as a factor. So the amount that I have moved the tool back out as a factor. And I could then take those 0.161 and add this to this addendum. Which will give us then our addendum coefficient. I have previously showed you, or we can also double check if this is correct. And we can see we get the same root diameter again. So I've showed you previously the more simple method by just reading out the root diameter. But of course, if you do it this way, maybe you can do it once so that you can be more certain that you really understand how this additional machining stock, how it was generated, how it is related to this profile shift of the pre-machining tool. I will now look at another question. The question is if we can save the curve of a profile at maximum and minimum tooth thickness in a single KISSsoft file. What we can do is we can save this. You can save the graphic of this. We have seen in the tolerances tab here we can choose at which tolerance situation we want this graphic here. So for example, if I take my pre-machining step, so I'm only going to look at this one here. If for the tolerance field for tooth thickness, I would choose, let's say, the minimum value first. If I run a calculation, now this would be the situation at minimum tolerance. And I could now go in here and save this curve. So the tooth form after pre-machining, I can save this one, call this minimum allowance. I will choose a slightly smaller line width so that we can easier see the difference afterwards. And I will use a black continuous line. So now this one is stored. And if I want to compare this to another tolerance situation, so I will choose the maximum tooth thickness now. And I can already see that this black line is at a different position. I could also save this new tooth form again. So this is at maximum allowance. And let's choose a red line. I will also make it only one, thickness of 1. And I can see now these two different tooth forms that I would get for maximum or for minimum allowance. So by adjusting the tolerance field in the tolerance tab, you can create different tooth forms, and by going into the options and selecting a tooth form and saving it, you can save it and then compare it to another tooth form. So I will end the remaining questions. We can answer them, or we will answer them through email. You can also, if you have any further questions, you can also send us additional emails either to support or to our sales team. I would like to thank you very much for participating in this web demo. And if you're interested in an extensive training on one of the KISSsoft calculations, you will find a list of current training topics and dates on our website. I wish you a pleasant day and see you next time.